Okay. Brois is here. Good morning to everybody. Welcome to the second day of the workshop, and welcome to this session, which is dedicated to 3D printing again, as the last one. And the first speaker is Charles Dapogny. And so we can start. Please.
Okay, so thank you very much, Emiliano. Thank you very much to the organizers for inviting me to this workshop. So indeed, I will present a work dedicated to shape optimization in the perspective of additive manufacturing that was done together with Grégoire Allaire from École Polytechnique and Rafael Estevez, Alexis Faure, and Georgios Michailidis from the Material Science Department in Grenoble. All right, so can you all see my screen?
Yes.
So just a few words as a starter to put things in the context. So shape and topology optimization techniques, they have been used for decades by engineers, and they have aroused a tremendous enthusiasm in this field. One thing that is currently reproached to these techniques is that they generally deliver too complicated designs to be manufactured. So, for instance, here is an example of an optimized design for whatever criterion that is made of very, very thin bars that would be very difficult to assemble. But this is why there is so much hope in the recent additive manufacturing techniques, because they are alleged to be able to assemble shapes with an arbitrary level of complexity, such as the one that is printed here in metal. But this comes at the expense of new constraints, because these additive manufacturing techniques impose new constraints on the design that are processed, that should be modeled and incorporated into the design optimization process. So here is a short outline of this presentation. So I will first discuss a few generalities about additive manufacturing that probably you are already aware of, especially after the first day of the workshop, but they will be needed to construct our mathematical models in the sequel. And then I will present the structural optimization, the model structural optimization setting of the presentation, before discussing the two constraints, the two types of constraints imposed by additive manufacturing techniques that I would like to discuss in this presentation. So, as a starter, let me just remind that additive manufacturing techniques, additive manufacturing or 3D printing is just a common label for a whole range of techniques that all share in common the fact that they begin with a slicing stage, according to which the shape to be processed, like here, is sliced, is decomposed into a series of horizontal layers. And each layer is then produced one atop the other by means of the selected technology. And so the different additive manufacturing technologies differ actually by the means that each individual layer is assembled. So two of these, perhaps two of the best, of the most used, of the most widespread techniques to assemble each individual 2D layer are first material extrusion methods, such as this one. So probably you've already met FDM methods. And so these methods, they act by direct deposition of rasters of molten filaments. And so these are the methods that are generally used to process plastic. And so another type of method that is usually used to process metal is electron beam melting. So in this type of techniques, each layer is built by first spreading some metallic powder within the build chamber, and then melting selectively the regions corresponding to the 2D layer by means of a laser beam, like here. Okay, so let me first come to the first issue that is currently encountered by additive manufacturing techniques is I guess that you are quite familiar with this one, is the overhang issue, the so-called overhang issue. The fact is that all additive manufacturing techniques, they experience trouble when they assemble regions which show large overhangs. So a overhang is a region of material that is hanging over a void. So this is, for instance, a short overhang, and this is a large overhang. So the reasons why shapes experience difficulty, additive manufacturing techniques experience difficulties in assembling overhanging regions may differ from one technique to the other. For instance, in the case of FDM processes, that are material extrusion methods that I have discussed just before, the reason is clear. since you deposit rasters of materials one on top of the other, if you would like to construct such a pattern, then it would amount to depositing material of a void. So of course, this is not doable. In the case where you are using powder bed methods, the reason why overhanging regions are bad is not that clear, is not that obvious, but it's due to because you have some metallic powder below the overhanging region. But the fact is that this metallic powder has a very low thermal conductivity, which makes it difficult to evacuate the heat of the molten region, which is here. So in practice, this will cause residual stresses inside the overhanging region, which upon cooling will cause warpage of the part. So here is an example of a warped part upon cooling over an overhanging region, for instance. Because the heat cannot evacuate properly because of the presence of a large overhang and the presence of low conductivity metallic powder beneath. So the most common strategy to deal with this overhang issue is usually to construct a sacrificial scaffold structure at the same time as the shape, meaning that some pillars are constructed to ensure to anchor the overhanging regions to the base plates. So this is what is generally done, but this is a little bit cumbersome because this uses more material that should be removed at the end of the process. So generally, this is a process. Removing this support structure at the end of the process is a little bit cumbersome, and it can be altogether impossible, for instance, if you have inner cavities inside the shape, for instance. So it would be actually better to design, to optimize the designs so that they can be used for their final use, for their intended use, but they are naturally overhang free. So this will be one of our main tasks in this presentation. So the second problem caused by additive manufacturing techniques is the anisotropy of the effective material properties inside the shapes assembled by additive manufacturing. The fact is that in parts produced by additive manufacturing, the material properties that are observed do not exactly match those predicted by theory. And the main reason for that is that there are some regions that melt and cool together and some regions that melt and cool apart from the others due to the particular assembly process. And the regions that melt and cool together, they have stronger bonds between each other than regions that melt and cool at separate times and in separate regions. So this is why these effective material properties are generally anisotropic, and they depend on the pattern used for assembling each 2D layer, for instance. And this pattern depends on the shape itself in general. So it's a crucial challenge to try to model and incorporate this behavior into the design optimization process. So here are two examples, for instance. So this is a typical pattern for assembling each 2D layer in a FDM process, in a material extrusion process. So first, the contour of the layer is carefully printed by several layers of material that you can see here. And then the infill is built by using some predefined, some raster with a predefined orientation. Here is another pattern for printing a 2D layer here. And first, you print the contour. You first print the contour of the layer, and then you go over all the layer by following the contour offsets of the shape. So let me come now to the structural optimization setting that will be studied in this presentation. So in this presentation, we consider linear elastic structures, that is mathematically shapes, meaning bounded domains in RD that are clamped on the part gamma D of the boundary and subject to traction loads F on the part gamma N of the boundary here. And so in this response, so this is how we describe the final use of the shape omega. And in this context, the displacement field is governed by the linear elasticity system, which is written over here. So in this system, there is up here the material properties are encoded in the Hooke's tensor A, which is written over here. So the Hooke's tensor, in general, just a small digression about the Hooke's tensor, since this will be used in our modelings afterwards. So when the material is isotropic, the Hooke's tensor reads like this, and it involves two parameters, mu and lambda, which are the Lamé parameters, which are not so much physical, but which are connected to very physical quantities that are the Young's modulus E and the Poisson's ratio nu by these formulas here. And so in a nutshell, the Young's modulus is just the force that you have to put to stretch a piece of material by a unit length. So the larger the Young's modulus, the more resistant the material is. The Poisson ratio is just a deflection in the transverse direction when you stretch a piece of material by a unit length. So in general, so when the materials are anisotropic, things get a little bit more complicated, and the material has different physical properties, so different Young's modulus, different Poisson ratio, depending on the direction. And in this case, for instance, the Hooke's tensor is just a general mappings from strains to stresses. And most materials actually have a special kind of anisotropy, which will be the case of the material that we'll consider here, and they are orthotropic. Orthotropic meaning that they have d principal directions. They have one Young's modulus per principal direction, and one Poisson ratio and one shear modulus for pair of principal direction. So here is the example of a concrete, of reinforced concrete, where you have a matrix of concrete with some vertical fibers of metal, for instance, and so the Young's modulus will be very different depending on whether you try to stretch or compress the material in the direction of the fibers or in the transverse direction. Here is also wood, which is a typical orthotropic material, which has different physical properties that you can see here, depending on whether you are in the transverse direction of the piece of wood here, or in the radial direction, or in the normal, or in the transverse direction here. Okay, so after this small digression, the shape optimization problem, the typical shape optimization problems that we'll consider will like this. So we minimize some function j of the domain omega over a set of admissible domains under some constraints, which will be meant to enforce the manufacturability of shapes by means of additive manufacturing techniques. And so these are the constraints P of omega that we wish to model in this presentation. So as for the objective function, it will be the compliance, the structural compliance of the shape in the use case, meaning once the shape has been manufactured, and which reads like this. So this is just for illustrating purpose, but other types of objective functions for describing the final use of the shape could be used equally well. It wouldn't change a thing to the purpose of the present presentation. And so we wish to model the constraints P omega, which enforce the constructibility of shapes by additive manufacturing techniques. So before we do so, let me just say a few words about how we theoretically and numerically intend to solve such shape optimization problems. So we use one of the possible methods to do this. So when it comes to solving such a constraint optimization problem, it's generally a good idea to have a knowledge of the derivatives of the objective function and the constraint function with respect to the variable, which is in the present case the domain. So in this case, we have to give ourselves a means to take derivatives with respect to the domain, and we select Adama's method to do so. So Adama's method, it amounts to, for a given shape omega, to describe variations of omega by pushing every point in the boundary of omega by a small vector field theta, meaning we consider variations of omega in the form omega theta, which is just identity plus theta of omega. So we just push every point of the shape omega by a small vector field theta, which parameterizes the variations of the shape. And so when it comes to considering actually we should define the derivative with respect to the domain of a functional j of omega as the derivative with respect to the underlying vector field of the function which to theta maps j of omega theta, which gives rise to the following Taylor expansion as would be expected of a classical derivative. So I won't enter into the detail of how we calculate shape derivative. This is not an easy matter, but it's a fairly classical matter in the literature, and especially in the optimal control literature. Just a small slide to add that generally this shape derivative has a particular structure which is written here. The j prime of omega in a direction theta writes as the integral of the free boundary, meaning the only one that we wish to optimize, of some scalar field which depends on the optimized function, and against the normal component of the deformation theta, meaning that at first order, only normal deformations of the shape will produce significant increase or decrease of the objective function. So for instance, when we consider the compliance, as is the case in our presentation, the shape derivative is given by the scalar field V omega, which is the negative elastic density energy, which is written here. So I could answer some questions about this, but this is a fairly classical matter, and so I will skip over details about this. So finally, this paves the way to a natural shape optimization algorithm. So if we take theta is minus the field v omega against the normal vector in the previous relation, this gives for a sufficiently small time step t that j of omega, which is pushed by theta along a small time fraction step here, is given by this formula, which means that we produce a small decrease of the objective function at first order. So this paves the way to a gradient algorithm for shape optimization. So at each iteration, we'll calculate the solution to the linearized elasticity system on omega, on the actual shape omega n. Then we'll calculate the shape gradient in the descent direction according to the previous considerations. And then we will push the shape omega n according to this velocity field theta n to get a new shape omega n plus 1 as identity plus theta n of omega n. So I completely skip under the carpet how we are doing this numerically speaking. Just in a few words, we are using the level set method for shape optimization that I could describe more extensively if you have some questions about it. But since this is a quite classical matter, let's say, in the literature by now, and I want to focus more on the mechanical modeling of additive manufacturing constraints, I will skip these technical details for the moment. So let us now come to the modeling and incorporation of constraints to prevent the formation of overhang features in the optimized shape, in the shape optimization problem. So there is a first naive attempt that we could do to model such geometric constraints. The idea, which is quite used in the literature, is to rely on the angle between the boundary d omega and the vertical negative direction to penalize the presence of overhangs. For instance, we could say, well, we could rely on such so-called anisotropic perimeters functional, which are just functionals which read as integrals of the boundary of some function of the normal vector to the shape, and this function being something that penalizes regions where the normal vector to the shape is close to be to the negative vertical direction here. So this would, for instance, account for a choice of a function phi like this. So this would produce positive values when n is close to the negative vertical direction, inside up to some angle nu, which is here, and 0 elsewhere, just to penalize these regions here. So this is a purely geometric functional. There is no PD involved in the modeling of this functional. And so we can calculate the shape derivative of this functional. So I will skip the details, but it's a little bit of calculus. And the good thing is that this is very easy to plug into the shape optimization framework that I have just presented. And it is very cheap in terms of computational cost, since there is no PD to be solved to calculate this objective function and its shape derivative. The bad thing is that it produces terrible results for some good physical reason that I will try to explain right now. And this will motivate the use of a more mechanical model for the overhang constraints that will come further. So why doesn't this geometric constraint, doesn't it work so well? The reason for that can be explained by a small example like this. So we consider the design of an MBB beam. The beam is clamped on the two endpoints on the two lower corners that are here, and a vertical force, is applied on the middle of the upper side. And so we try to minimize the compliance of the domain under some volume constraints. So first, we are not adding any constraints on overhangs or some such things like that. And so starting from the shape like here, we end up with this optimized shape, which is written here. And so we can see that, as expected, there are large overhangs in the upper part of the shape, notably. So these are the regions that are here. But we would like to prevent by adding some additive manufacturing constraints. So let's now try to add in some way or another the geometric constraint that I have presented just before. And this produces the shape that is given here. So this is obviously not what we would like to see as a means to prevent overhang features. And actually, the shape develops an oscillatory boundary And it actually did exactly what we asked for, meaning that, as you can see here, there are no parts of the region of the shape where the angle where the angle with the negative vertical direction is less than 45 degrees, as we have required. This is just because the shape develops a very oscillatory boundary, just to make the constraints, which is here, satisfied almost everywhere, except at some tips, at the small tips that are here, but which are not seen in the numerical evaluation of the constraints. So actually the minimization here has done exactly what we have asked for. And this just suggests that this is a bad idea to incorporate to understand overhang constraints. So thus, we will rely on some more mechanical model for the overhang constraint that I will present now. And so for this, we will rely on some short model for the building process. So in this set, we will need to understand the physical behavior of the shape during the building process. And so to this sense, we'll suppose that all the shapes that we consider, they are enclosed in some domain, some fixed domain D, which will account for the build chamber. So it's a box with capital H. And so we'll consider each intermediate shapes with intermediate H that will be produced during the assembly process. Meaning that we consider the shapes omega H when it corresponds to omega when it is erected up to 8 small h. So omega H will be the yellow part here. And the boundary of this intermediate shape is decomposed as the lateral boundary gamma H here. And the part that rests on the base plate, which is where the shape will be fixed during the assembly process, and the upper part of the intermediate shape. So this is just a model for the shape, not in the final use, where the compliance is evaluated, like I have presented before, but during the assembly process. So this is another model just for the assembly process. So now we model the physical behavior of the shape during the assembly process by means of the physical behaviors of each independent shapes during the assembly process. And these intermediate shapes, they are supposed to be just subjected to gravity effects, meaning that the elastic displacement during the manufacturing process of each intermediate shape is described by this linearized elasticity system posed on the intermediate shape, and where only gravity loads are exerted on the shape. So we consider then the self-weight of each intermediate shape, which is just the compliance of the intermediate shape omega H when it is submitted only to gravity. So this corresponds to this formula here. And so our manufacturing constraint, it will be an integral of all the compliances of the intermediate shapes in the course of the assembly. So it will be an integral of some quantity depending on the compliances of these intermediate shapes when they are subjected to gravity. So again, the displacement which is written here is not the displacement that was written before. The displacement that was written before was the displacement of the shape in the use case, with clamping regions and load regions that were different than those that are here. Here, the clamping region is the base plate, and there is no external load, only gravity. So we could actually use other models for the physical behavior of intermediate shapes. For instance, we could suppose that the main efforts applied on intermediate shapes is not gravity, but is the weight of the roller or of the machine that comes and deposits material on the upper side of the shape. In this case, this would amount to replace the U omega HC, the displacement of the intermediate shape with respect to the gravity load, by UHA, where some loads are applied only on the upper part, on a small layer, on the upper side of the intermediate shape. So this could correspond to this type of formulas that I written here. So this wouldn't change a thing in the model that we will present just afterward, but just to mention that we could use other physical models for the intermediate shapes. And so the mechanical constraints could also involve other physical effects. For instance, we could model with this so the cooling process inside during the assembly process by, for instance, replacing the elasticity equation describing the physical behavior of intermediate shapes by some thermal equation. So there is a recent paper by Grégoire Haller and Lucas Jacobsin, which takes into account this idea to model residual stresses inside during the assembly process. All right, so just a horrible slide to say that actually this self-weight manufacturing compliance here, or constraint, it is shape differentiable, and so we can calculate the shape derivative of this guy and come up and plug this into our shape optimization framework. So I'm skipping under the carpet. So I'm skipping the carpet the way that this is implemented into our shape optimization framework. So this is a little bit costly to evaluate because there are a lot of intermediate shapes to be considered, but there are some tricks to accelerate the calculation and make it reasonable to perform the example that I will show on a standard laptop. Okay, so now let us come to numerical examples. So we retrieve this MBB beam example that I have talked about, where the shapes in the final use case, they are clamped on the two lower part of the boundary here, and a force is exerted on the upper side of the boundary, on the middle of the upper side, like this. And so we now solve the constraint optimization problem of minimizing the compliance of the domain in the use case with respect to a volume constraint, and with respect to a constraint on the manufacturing compliance, the manufacturing constraint that I have just presented. Okay, so here is what we obtain without manufacturing constraints. So this is the same shape that I presented at the beginning of a few minutes ago. And here is what happens when the threshold for the self-weight manufacturing constraint is made stricter and stricter. And so we see that the shape tends to develop less and less overhang. The optimized shape has less and less overhangs. So actually, we could be a little bit critical here, because the result here, even with the most critical, the most strict threshold for the manufacturing constraints, it gives good results, but not perfect results. There still are some regions with overhangs, notably these two regions that I'm showing here. So actually, there is a perfectly good reason for that, is that there are two reasons for that. First, we see that the use of this manufacturing constraint, it favors structure which have stronger lower parts. And this is because a part where a overhang is happening in the lower part, the overhang will count in every intermediate shape in the integral which is given over here. So it will be it will penalize a lot the value of the overhang constraints. Whether if the overhang is present on the upper side of the shape, then it will only count on the latest, on the highest slices of the shape, and it will not impact too much the value of the function proportionally. Actually, there is another very good reason why there still are some large overhangs, even with the most strict threshold for the manufacturing constraints, is that our model is very crude actually for the manufacturing process, and that we do not see regions which are completely horizontal. Actually, we consider that each region is deposited at once, and so we assume that each layer of material is assembled instantaneously, which means that a structure which presents completely overhanging region, completely horizontal region, is not too bad for our constraints, because before the completely flat region, we have this structure, which is not too bad actually for the manufacturing constraints, for the compliance. And then we will have this region where the part is not hanging over void, actually. It would be hanging over void if we were to consider all the intermediate stages of the construction of the layer, where we would see that the part is hanging over void. But here it's not hanging over void. So actually there is a simple trick to remedy this, is to replace our self-weight manufacturing constraint by that obtained when considering just a load on the upper part of the intermediate shape. So we replace the gravity by a load considered only on the upper part of the boundary, which physically speaking could simulate the weight of the roller over the shape. But this is just a way of seeing things. This is just completely artificial in our case. And in this case, this will penalize a lot regions like this, which will be very brittle when a load is exerted only on the highest region of the shape. So this is what we expect. And so let's do the same thing with the same example. And now that you see that the resulting shape is completely overhang free. So just a small example in 3D before we move to the other type of constraint that I would like to discuss. So we consider the design of a 3D bridge. So the bridge is clamped here in the four lower corners, and some load is distributed on the upper side of the shape, mimicking, for instance, pedestrians walking over the bridge. And so we try to minimize the volume of the shape with a constraint on the compliance in the use case, and also on our manufacturing compliance, which is written here. So since we know that there will be a deck of material in the upper side, we will print the shape from the top to the bottom, so upside down. So here is what we obtain by solving this program without manufacturing constraints. So the optimized shape is this, and it is printed like this. So starting from the top and going from the bottom like this. And we can see that there are large overhangs in this region that we would like to remove by using our manufacturing constraints. So here is what we obtain with a manufacturing constraints. And we can see that the optimized shape now, when we look at the printing pattern, which is here, is now completely overhang free. All right, so now I believe I have just some time to jump to the other type of constraints related to additive manufacturing that I wanted to discuss, which are related to the material anisotropy inside the shapes assembled by additive manufacturing. So let me just remind that these properties are influenced by the path of the machine tool during the assembly of each 2D layer. And so to try to appraise this behavior, we just consider one 2D layer. We just work in 2D for this study, and we'll consider what happens in the assembly of one 2D layer. And actually, so this 2D model amounts to the assembly of one 2D layer, and a small increment of this model will allow to deal with the 3D case, as I will explain in the following. So we will propose two models for considering the printing pattern of each 2D layer. And these models will rely on the notion of sign distance function, and that I would like to say a few words about just as a starter. So I just say a few words about the notion of sign distance function to a shape. So the sign distance function to a domain omega is just the Euclidean distance to the boundary with a positive sign when we are outside and negative sign when we are inside. So this is a graph of the sign distance function to the two-circle shape, which is given here. So when it comes to the sign distance function, there are a certain number of quantities of interest. The first one is a set of projections. So when we consider a point inside RD, the projections of this point onto the boundary is just the points that minimize the distance from X to the boundary. When there are several such points, then say that X belongs to the skeleton of the boundary d omega. So the skeleton is a set of points which have at least two projection points over the boundary. And when X has a unique projection, meaning when it doesn't belong to the skeleton, then this projection is denoted like this. So here is a small drawing. So we have a domain omega here. The skeleton is a set of points here. A point X prime in the skeleton here has at least two projection points, which are those given here, which minimize the distance from X prime to the boundary. And the point which is X, which is outside the skeleton here, has a unique projection point, which is represented here. So a few more useful properties is that in general, the sign distance function is differentiable at every point outside the skeleton, and the gradient reads like this, meaning it's oriented in the direction of the ray between X and the projection point. In particular, and also this gradient as unit norm. So when, in addition, omega is of class C1, we can prove that this quantity, the gradient of the sign distance function at X, is exactly the normal vector at the projection point. And when omega is a little bit more regular, meaning at least of class C2, then d omega is also of class CK on the neighborhood of on the tubular neighborhood of the boundary. So here is an example. Here is my domain omega. The skeleton is here. The isolines of the sign distance function are those depicted here. My point X is here, and the gradient of the sign distance function, which is orthogonal to the isolines of the sign distance function, has the direction of the ray between X and P omega of X. And this also matches with the normal vector to the projection point at the normal vector at the projection point. So some final properties of the sign distance function is that first, the normal vector and the tangential vector field can be extended to any point outside the skeleton by just taking the point at the normal vector and the tangential vector at the unique projection point. Also, it is possible, it's a little bit technical, but it's perfectly doable, to calculate shape derivatives for the same distance function, meaning taking for a given point x in RD to look at the shape derivative, mapping which to omega associates d omega of x. And it's also possible to calculate shape derivatives of integral functionals, which depends on the shape omega via the same distance function. All right, so let's now come for the different models for the printing patterns. So the first model that we will consider is the so-called cross-pattern model. So according to this model, the layer, the 2D layer, is constructed by first printing carefully the contour of the layer, and then several offsets of this one, just to carefully follow and fit the contour of the layer. And then the infill is the bulk of the shape is filled by an infill with a predefined orientation, meaning this is an horizontal infill, meaning some rasters of material with a predefined orientation, and with a predefined density, meaning spacing out between the rasters. So this is the air gap between the rasters that are here. So in this case, the material properties are to be compared to the expected material properties, for instance, of a cast if the shape were to be produced by casting. And in the crossed region, we expect the Young's modulus will be like the one of the material of the reference material in the tangential direction to the shape, in the tangential direction, because the material is melts and solidifies together. And it will be weaker than the reference material, than the reference Young's modulus in the normal direction, since there are several rasters of materials that are melted and cooled apart from the other. So there will be some bubbles of air between the different rasters, which makes the normal Young's modulus weaker, actually. And in the infill region, then you have a tangential direction to the rasters and a normal direction to the rasters. And for the same reason, we expect that the Young's modulus will be stronger will be that of the reference material in the tangential direction to the rasters and weaker in the normal direction to the rasters. So how do we build this Hooke's tensor then? Then we separate three regions in the space, in the computational domain D. There is a crust where the sign distance function to the domain omega will be smaller than some epsilon in modulus. So this will be the region which is here. There is the bulk region where the sign distance function is negative, is more negative than minus epsilon, and the void, which is the rest, which is here. And so we glue together three tensors, one for the bulk properties, one for the cross properties, and one for the void properties, which depends on with some interpolation function, which depend on the sign distance function to the shape, just to locate in which region where we are. And the material properties inside the cross, they also depend on the shape via the normal vector, which is here, which encodes the difference between the tangential and the normal properties of the material. All right, so now we come to the second model for the assembly properties, which is the simplest offset model. And the offset model, when we print, for printing a 2D layer, we'll print the shape by following the contour offsets of the shape until the building of the layer is complete, like this. So for the same reason, we expect the Young's modulus in the tangential direction at every point will be that of the reference material, and that the Young's modulus in the normal direction will be weaker. Again, to model this mathematically, we will glue together two tensors, one for the bulk and one for the void, which is here. And the tensor for the bulk will depend on the normal vector to the shape according to the previous intuition. Okay, just one final word before passing to examples and concluding the talk, just to mention that this could be easily extended to take all the 3D case, because if we were to consider several layers, then we just had the fact that in the three-dimensional Hooke's tensor, there is a weaker direction. The tensor would be orthotropic with principal directions, the tangential direction to the rasters, the normal direction, and the 3D direction, in which the material would be weaker also, because this corresponds to material deposited and solidified separately from one layer to the other. So just this horrible slide to try to convince you that the shape derivative originating for the compliance associated to these new material properties which depend on the shape, it can be differentiated with respect to the shape. So this is the horrible formula that is given here, just to mention that it's possible to calculate this derivative And you don't want to see the technical details. Nothing complicated, just a lot of calculation. So let me skip to numerical example to conclude. So we consider a 2D cantilever example, and the cantilever is clamped on the left-hand side of the boundary, and we accept a traction on the right-hand side here, and we try to minimize the volume of the shape with constraint on the compliance of the domain. And taking into account that the shape will have the material properties of either the offset model or the cross-pattern model. So here is how it goes. So this is the optimized design in the material to be to have everywhere the reference material properties. So this is the classical cantilever figure. And this is what we would obtain if we were to consider that the material will be printed by the contour offsets. So this is the optimized shape in this case, where the printing pattern is given here. And these are also the optimized shape that we would obtain if we were to consider that the material is printed by the crust pattern model with some very large density, meaning a very small air gap between the rasters. So this corresponds to a shape printing with an isotropic crust and an isotropic infill with different material properties. This is the shape produced by an isotropic crust and an anisotropic infill with horizontal rasters. This is the anisotropic crust with the model that I presented with a tangential direction which is strong and normal direction which is weak, and a horizontal direction for the rasters, anisotropic crust and isotropic infill. And what we can see is that the material tries to take into account the fact that the shape has to be strong in the tangential direction to make these small roundings near the place where the forces are applied. So it takes into account that the fact that there is a larger tangential resistance in this cross-pattern model than the normal resistance. This is why there is a rounding here in the point where the forces are applied when the cross is anisotropic. So here is what we obtain with a smaller density. So of course, the volume will be extended. So there will be a larger volume, and again with a larger a smaller density of the shape. And so we can see again that there is this rounding, which is even more obvious in this case here, in the case where the crust is anisotropic. So one final example is that of a 2D MBB beam. It's more or less the same example as I presented in the first case of overhang issue, but we have in this case two loads which are given here. And so in this case, we try to minimize the volume of the shape with respect to a constraint on the compliance. And here is what we obtain in the molded situation, if the shape were to produce with reference material properties everywhere, in the case where the crust is anisotropic and the bulk is isotropic, in the case where the crust is isotropic and the bulk isotropic, in the case where the crust is isotropic and the bulk is anisotropic, with the direction of the rasters produced here. And we see that the shape tends to produce, to expose the force of the upper side here to resist bending due to the application of the two loads on the upper side. So that's all I wanted to present. And let me again thank you for this invitation and for your attention. Thank you very much.
Thank you, Charles. And okay. Silvia is clapping, virtually clapping also. And okay, so please, Luca, can allow everybody to unmute themselves.
Yeah, already done.
Okay, for questions. If you have questions, you can raise your hand or write your name in the chat window. And okay, in the meantime, we have time. Yes, maybe we have time for a short question. And I have a curiosity rather than. Okay, Nicola. Okay, you can choose the color of your hand also. Okay, so Nicola, please.
I don't know actually how I chose the color of my hand. It was like this at the very beginning. Anyway, thank you for your presentation, Charles. It was very interesting. And I wanted to ask you a curiosity about the manufacturability constraint that you imposed, simulating the building chamber. I guess that you at first suppose a building direction of your. So how can you include the optimal choice of the building direction in your framework, if it is feasible or
All right.
I don't know.
Well, I don't know. You are totally right that you choose a building direction, and you could try to optimize. It would be completely relevant to try to optimize this build direction. I don't see any easy means by which it could be incorporated into this framework.
Yeah.
By coupling this with the small model for simulating the building process, I don't quite see how you do that. I know that there are some works for simulating, trying to optimize the building the orientation of the build direction, which rely on more geometric criteria. For instance, I think there is an article by Benny Bogosel and Grégoire Haller addressing this issue, in particular, among other articles probably. But they rely on more, if I'm not mistaken, they rely on more geometric criteria for optimizing this build direction. I don't quite see any easy means by which we could couple this with the model here. You would have to take derivatives of the slices in some sense with respect to the orientation of the slices. So it seems a bit. I don't quite see how we do it.
Yeah, I'm working on building directions for future with geometry, but your approach seems more robust, I guess. I don't know. It's a simulation of the whole process, so it would have been interesting to see if it could have been incorporated.
It's possibly more robust than geometric criteria, but it's also it comes at the expense of more complicated modeling and also higher computational costs than purely geometric criteria.
Yeah, thank you.
Thank you.
So, okay, maybe Maurizio has a question.
Hello, good morning. Thank you for the presentation. I have a curiosity regarding the way you apply the level set method. So
yes.
you derive a vector field which is moving all the points at the boundary, but this is a numerical reconstruction. So at the very end, you could end with a vector field which has a lot of discontinuities, which is not strictly allowed in the level set method. So how practically you manage this difficulty? Because all the vector fields that are coming out in your process are derived numerically. They are not formally defined by an algebraic definition. And the second point is, okay, so I have another question then regarding the gravity constraint versus the geometric constraint. Because in the gravity constraint, I don't see how you manage this, the material, and then how do you consider the fact that the hanging part is in metal or is in plastic or is in clay, which makes a big difference there.
Yes. Okay, so as for the first question, you're totally right that in general, so the field, everything in the shape gradient is encoded in. So the descent direction is this one. So it depends on normal vector to the shape and this scalar field here, which depends on the solution to the linearized elasticity system or possibly an adjoint state. So this may be not discontinuous, but not very regular in general, as you mentioned. Also, there is another point is that you have to extend this formula to the whole computational domain, because for the practice of the level set method, you need a vector field which is defined everywhere inside the computational domain. Actually, we have this. We regularize the descent direction in the same time as we extend it to the whole computational domain in a single stage, which is using the so-called Hilbertian trick. This is more or less the equivalent as sensitivity filtering in the context of density-based methods, which is just changing scalar products when identifying a gradient for the derivative, which is written here. So this allows to infer smoother gradients, which are defined on the whole computational domain associated to this derivative, which is here. So I don't know if this answers your first question.
Yeah, okay, okay. And this is described in your paper?
This is a quite classical issue in the structural optimization thing. So I could send you some references about this, for instance. This is not something that I have invented.
Many thanks.
I could send you some references if you are interested. This is not something I have invented.
And regarding the gravity constraint?
Yes. So the material property, the material properties that just come into play. Okay. Yes. The material properties they come into play by the way the displacement of the intermediate shape depends on reacts to the application of gravity loads. So if you have steel inside of plastic, then the Hooke's tensor here will have a larger Young's modulus, so it will resist better gravity effects. So the material properties are encoded in the Hooke's tensor, which are here. And for the purpose of this particular application, I considered indeed that the material is given and there is no dependence on the material properties on the shape, as I did in the second part.
Okay, thanks.
Thank you. I think you are muted, Emiliano.
Oh, sorry, I was muted. Okay, so sorry, Silvia, there is no time for other questions. So I have unraised your hand. And let us move to Nicola Ferro, the next speaker. And Nicola can share the screen.
Yes. Can you see anything?
Yes.
Okay. Is it moving? Yeah, I guess so.
Yes.
Okay. So thank you for the invitation. I am Nicola Ferro from Politecnico di Milano, and today I will present my work on an isotropic mesh adaptation for 3D printing oriented structural design, which actually is a joint work with many collaborators. In particular, my PhD advisors, Simona Perotto and Stefano Micheletti, back in my PhD days, and also master's thesis students and many other collaborators. So thank you again for the invitation. And I want to start with a brief introduction of what I will discuss about today. And basically, you know, because many people have already talked yesterday and today about design of structures. And in this framework, there are mathematically robust techniques that can be useful in the framework of design optimization, involving different goals and design of interest. In particular, from a mathematical viewpoint, you can choose between different methods, for example, level set methods or density methods, to address the problem of optimal design. And in this specific talk, I want to address a particular numerical scheme that we developed that turns to be adaptive and versatile for a structural design problem. In particular, I will present the coupling between structural shape and topology optimization together with an isotropic mesh adaptation. For the design, for the design optimization part, I will deal mainly with topology optimization. So how to modify the topology of a design domain to comply with given requirements. But I will also introduce briefly the concept of shape optimization, as already the previous speaker had talked about. So how to find the optimal shape of a structure, again, complying with specific constraints. First of all, for the outline of my presentation, I will introduce the topology optimization in the density-based approach scheme. Then I will detail how the anisotropic mesh adaptation works in a metric-based context, and I will couple it with the topology optimization problem, and I will present some preliminary results that were encouraging enough to move to different applications. So the second part of my talk is completely dedicated to applications, and in particular, I will present how the anisotropic mesh adaptation and topology optimization coupled together can be useful for robust structural optimization, metamaterial design, performance constraint design in a multi-constraint, multi-objective design framework, and also how to introduce AM constraints in the topology optimization problem. Finally, I will present, of course, my conclusions and the future developments of this research. So starting with topology optimization, as I told you, and as you may know for sure, the goal is to find the better topology inside a design domain that can guarantee that the new design structure can comply with specific constraints involving the physics of the problem that we are modeling and the design that we want to obtain. There are several choices in the literature that we can exploit in order to design the structure, so how to identify inside the design domain where to have voids and where to have full material. And among them, level set methods and density-based approaches are among the most widespread. Today, I will deal with the SIP method, which is a density-based approach. And in particular, I introduced the density variable rho, which takes value in 0, 1, identifying the topology. In particular, I assume that rho is equal to 0 where we have void, so in the portions of the domain where we have void, while rho is equal to 1 where we have presence of full material in the design domain. In this breach test case, you can see that the alternance between blue void and red material is such that we can identify the topology. Nevertheless, the density variable is continuous, so all the intermediate densities are accepted. So what we have to do in the same framework is to penalize the intermediate densities to appear in order to push our final configuration to be a black and white configuration, so void or presence of full material. How can we do that? A standard topology optimization problem reads as the minimization or the maximization, if you prefer, of a given functional, obeying some particular constraints. In particular, in the problem on the top of the slide, you can see that it is obeying some given state equation in weak form. Also, we impose two other constraints. The first one is a constraint on the final volume occupied by the design. In particular, we impose a reduction of the volume of the initial domain, and also we impose a box constraint on the value that the density variable can attain. Rho can take value between 0 and 1, as I told you. In order to have a well-posed problem, I impose rho to be between rho mean and 1, so that we do not have degenerate state equation, so no problem with the solution of the finite element problem. Here, the objectives that you can choose are very diverse. For the toy problem that I will present right now, the main objective of the so-called minimum compliance problem is the compliance, so the minimization of the work done by the external forces on the body. And this is actually equivalent to the maximization of the stiffness of the structure. So it is also a physical meaning to be interpreted. When we impose a given behavior, a given physics to the problem, we have to impose a PDE. In particular here, we use a modification by means of the density variable rho of the standard linear bilinear form for the linear elastic equation. And as you can see, the stress tensor is given in terms of the density rho. So we modify the constitutive law in order to in order for the density to appear and to modify the topology in the optimization problem. So here we modify the Hooke law by means of a power law penalization, rho to the power of p, where p is an exponent to be chosen and is responsible for the penalization of the intermediate densities. So when you talk about a black and white configuration, you have to decide which p to choose in order to have a proper penalization of the intermediate values of the density. This is all the machinery for the toy problem of minimum compliance problem in the SIP framework, which is known to suffer from some issues. In particular, we do not have uniqueness of the solution a priori, because we cannot prove the convexity of the problem. Also, the problem is mesh dependent, so we have to choose a proper discretization, and if we change it, we can expect different results in our numerical simulation. So many contributions deals with the additional filtering of the solution in order to constrain the space where we look for our solution, or we can add some regularization terms. Also, in particular case, we can turn to adopt discretization for the specific problems that we are dealing with. So there are several options that you can propose in order to heal some of the problems connected to the modeling and to the numerical discretization of the topology optimization in the SIM framework. But today I will present an idea that is about more about the numerical discretization. In particular, what we want to do is to couple topology optimization as it is stated so far with an isotropic mesh adaptation in order to have an automatic framework that can address structural optimization and that can deliver some good results in terms of quality of the structure, quality of the design, and quality of the mechanical performances obtained. Here I will start detailing how an isotropic mesh adaptation works and what we want to do. And as you may know, mesh adaptation works by changing the computational grid that we are using for the simulation of a given PDE or a given problem by means of modifying local operations on the mesh in order to have a better discretization in correspondence of given features of the solution or important features of the solution that we want to track, to identify, to better discretize. So we want to limit the computational burden because we can coarsen the mesh and refine only where it is needed. At the same time, we want to guarantee accuracy to the solution. We can turn to different approaches. In particular, if we let the physics described in the problem guiding the mesh adaptation, we can turn to isotropic mesh adaptation or to anisotropic mesh adaptation. If we choose isotropic mesh adaptation, what we have to do is to define for each element K the size, because all these shapes are regular. So the only quantity that we need to identify is for each element K the size, the diameter HK. Instead, when we talk about anisotropic mesh adaptation, we have to take into account more quantities. In particular, the elongated element that we are dealing with can be determined in terms of size, shape, and orientation that can be changed throughout the iterations. So we have to determine more quantities. In particular, we have to identify some geometric quantities related to the element K that here I call lambda and R. And I will give you more details what they relate to later on. Starting with the isotropic setting, which is the starting point of our procedure, we employ a Zienkiewicz-2 estimator type for discretizing the estimating the H1 norm of the discretization error associated with the density variable. Why are we doing so? Because we want to identify by means of a proper estimator that we call eta, the regions, the portions of the domain where the error is big and where the error is low. And in particular, we want to refine the portions of the domain where the error can be too large, and we want to coarsen the portions, the mesh in correspondence of the portions of the domain where the solution is flat, does not present any particular issue. So if we let our estimator eta guide the procedure, we are able to track the H1 semi-norm error or norm error estimation. How can we do that? We try to compute the estimator eta, but we understand that while the discrete gradient can be computable, because if we employ, for example, finite elements, it is possible to compute the discrete gradient, the exact gradient is not computable. So we cannot actually compute the H1 semi-norm of the discretization error. So what we can do is to resort to a recovery procedure where we substitute the exact gradient by means of algebraic modification of the discrete gradient. So the estimator now can be computable if we substitute the exact gradient by means of an operator P applied to the discrete gradient. That is now fully computable. In particular, the operator P responsible for the recovery operation can be chosen in different ways, and in this particular case is a area weighted of the discrete gradient that can be easily computed and turns to be efficient. But this procedure works in the isotropic setting, and what we want to do is to move this machinery as it is to the anisotropic setting. And we actually can do this if we identify how the anisotropic setting can be described. So what we have to understand is that if we have a reference element k hat, we have to move to the generic element k, and we have to describe all the geometric properties of the new element k that now can be elongated, so can have different sizes, different shapes, different orientation in the space. We consider the affine transformation from the reference element to the element k. In particular, this can be written as the product of a matrix nk plus a shift vector. And by means of spectral decomposition and polar decomposition, we can identify that the matrix nk can be decomposed in terms of some matrices that contains the geometric properties that we are looking for. In particular, lambda k contains the semi-length of the axis of the ellipsoid circumscribed to the element k, while the matrix Rk contains the direction of such semi-axis. So once we are able to characterize those two matrices, we are able to determine the shapes, the size, and the orientation of the element k for any k in the mesh. And that's what we want to do. We want to use the machinery, we want to use the estimation eta in order to drive the adaptation procedure. So in order to move from the estimator eta to the quantity that we want to find for each element k, what we have to do is to mimic what we have done for the isotropic setting. So we define an anisotropic error estimator, which consists in the projection of the error estimation onto the anisotropic directions. In particular, here you can see that there are some projections of a given quantity of a given matrix H that is scaled by means of the semi-length of the axis. This scaling is useful in order to guarantee the consistency with the isotropic case. Here, the matrix H has an input which is the recovered error. So again, we compute the error associated with the discrete gradient of the variable rho. And in particular, we can do that by introducing a recovery operator P, which again turns to be an algebraic manipulation of the discrete gradient. And the matrix H here is a weak Hessian that gives us the final form for the estimation. Now, what we want to do is to complete the procedure in order to compute the values associated with the new adapted mesh that we want to generate. And basically, we impose some requirements on the new mesh. We want to control the global error associated with the discretization. So we impose that eta should be less or equal than a given tolerance by the user, defined by the users. We also want to equidistribute the local error onto the mesh elements in particular. So we impose that the local contribution eta k should be equal to the tolerance divided by the mesh cardinality. So each element can contribute in the same way in the error estimation. And finally, we want to minimize the total number of elements in order to limit the mesh cardinality. And to do that, we want to maximize actually the size of the element. So the minimization of the mesh cardinality is equivalent to the maximization of the area of the volume of each new mesh element that we are designing. If we impose all these constraints or these inequalities and the equalities and liquid distribution criteria, we end up with a local optimization problem. So we have to minimize the total number of elements. We have to impose some constraints on the geometry. For example, the directions of the semi-axis should be orthogonal, and also we impose the equidistribution of the tolerance. If we write down this local optimization problem, we end up to have an explicit solution, so we can compute the values, the optimal values for the geometry of each single element k by means of eigenvalue, eigenvector computation. So we are able to compute R1, R2, R3, the directions, and lambda 1, lambda 2, and lambda 3, the lengths of the semi-axis of the ellipsoid circumscribing the element k. This should be repeated for all the element k, but this can be done automatically and gives us the so-called metric that can be fed to the metric mesh generator that one can employ in order to generate the new adapted mesh. So we start from a mesh THK, if you want to use a superscript k for identifying the iteration, we compute the density variable rho, and then we compute the new metric and we generate the adapted mesh. So this is how briefly our pipeline works. And here I show some first numerical results. The first one in 3D that we obtained that were very satisfying. And for the cantilever and the dome test case, you can see that we have different geometries, but in both cases, the mesh is well adapted to the interfaces between void and solid material. This is because the estimator is capable of identifying the portions of the domain where the error can be very high, and in particular, the error can be very high in presence of the jumps of the interface between void and full material, and there applies a directional refinement and an isotropic refinement that follows the directionalities of the boundaries of the structure and coarsen all the mesh elements where there is no need of having a full resolution. So at the very end, your structure has a very high quality in smoothness of the surface definition, and also a limited number of elements to be employed in the finite element computation. So what are our takeaway tips for this first part? Is that mesh adaptation, and I'm telling you this now, trust me, does not have any considerable overhead to the simulation, because mesh adaptation amounts to 3 or 5% to the overall CPU time, because the topology optimization problem, especially in 3D, is very costly, can be very costly. So the mesh adaptation, metric computation and mesh adaptation is not very relevant in terms of CPU time. So this is a good property because we are adding quality and we are not wasting too much time in it. The algorithm delivers smooth structures with a reduced employment of filters or regularization techniques, because so far we didn't add any filtering or any massive regularization technique. And what you actually can do is to take your structure, your surface definition, and you can determine an STL file that can be actually sent to the 3D printing process. So here you can see that we can actually print without any filtering or post-processing the structure that we obtain. And finally, maybe one of the most important features of this procedure is that this technique is application independent, because we so far have only used the design variable that we called rho, and in this case is the density variable. But in all the topology optimization approaches that you can think of, if you have a design variable and you want to apply this machinery, it works and it identifies the contour where the design variable has a steep gradient. So this procedure is application independent. And to convince you about this, I will now show some application of where mesh adaptation together with topology optimization has been applied. And maybe I can give you some ideas. And here starts my second part of the presentation about applications. So I will firstly dive into robust structural optimization. That is the second task that we try to do with topology optimization and mesh adaptation. Basically, what we saw is that topology optimization works in reducing the volume that we are considering. So we have we can design lightweight structures, but at the same time, if we compare the mechanical performances of interest between the full material configuration and the reduced material one, we can have a deterioration of the mechanical properties that one can be interested of. For example, if we consider the compliance, it is straightforward to understand that the compliance of the full structure is less than the one associated with the reduced one. So here, the main feature of topology optimization is the, as it is presented right now, is the mass reduction. But if we can consider also a mechanical performance, we can see that we have some work to do in order to have better performances also from the mechanical viewpoint. On the other hand, as the previous speaker already introduced to, we can use the shape optimization that in a particular configuration can be formulated as a mass fixed optimization. We can fix the mass of the structure that we are designing, and we can modify the external boundaries of the domain in order to comply with given constraints in order to minimize a given feature of interest. In particular, here we can fix the mass of the structure, and we can reduce the compliance. So we can see that both the techniques have different pros and different cons, because we would like to have structure characterized by a lightweight, but also we would like to have it very stiff. So what we thought about was to couple sequentially topology and shape optimization, basically starting with shape optimization and then apply a topology optimization step in order to obtain lightweight structures by means of topology optimization, which also are more performant by means of shape optimization. And this can be seen by the numerical results, because if we apply topology optimization in these two 3D test cases, which are a bridge and another cantilever beam, you can see that we have a mass reduction with a deterioration of the compliance. This also serves as a further illustration of how mesh adaptivity works in this context, because you can see that the mesh elements are well adapted to the identification of the boundary structure, and we are able to limit the number of mesh elements to be used in the configuration. But if we apply shape optimization first and then topology optimization, we obtain totally different structures, which are characterized by a different design domain, which has been previously modified by means of shape optimization, and are characterized by a mass reduction because we apply topology optimization later. Hopefully, we can also reduce the static compliance that we are considering. Why that? Because the first step of shape optimization can reduce the compliance, and topology optimization can reduce the mass, also increase a little bit the compliance, but we can try to see if there is a balance so that we have the best of both worlds. And actually, in some configuration, this can happen, because we can see that if we apply only topology optimization, we have an increase of the compliance in the bridge and in the cantilever test case. But if we apply geometric shape optimization together with topology optimization, we have a reduction of the compliance with respect to the initial one. Because again, we employ the two techniques together in order to use the beneficial effects of each one. And again, here, shape optimization and topology optimization coupled with an isotropic mesh adaptation guarantees us a high quality description of the design structure. Moving to another application, here I want to change a little the framework. In particular, again, I will can talk about topology optimization, but I want to change the point of view, because we can use our topology optimization framework for microstructural optimization, meaning that what we want to design are not the macroscopic design structure that we saw so far, but we want to design a unit cell that can be repeated periodically in space that can give us given properties. This is the concept behind metamaterials, which are structures that at the micro scale are represented by the repetition of given patterns, but at the macro scale, when you change the point of view, by means of homogenization, they behave as a material, but is a material which has engineered properties and maybe properties that cannot be found in nature. So if you try to use one of these already defined microstructure and you repeat them periodically in the space, and you change your point of view, you can have the so-called lattice materials, and you can see that they behave differently as the single material that they are made of. By means of the homogenization theory, so what we want to do is to move from the micro scale, so the design of the unit cell that we want to repeat periodically in the space, to the homogenized scale, so the macro scale where we see everything without magnification. And this can be done by using of standardized asymptotic expansion and by use of the homogenization theory. Again, what we want to do is to design things. In particular, here we want to design the unit cell. So again, we turn to topology optimization. So again, the problem can be written as a minimization of something by means of the density variable rho, and we can impose some given constraints. Again, here we impose some constraint on the volume fraction of our final configuration, and also the box constraints on rho in order to have a good description of the presence or absence of material. And the state equation now should be chosen in order to mimic what we want to do, in order to have the homogenization theory incorporated. So in order to see how the two scale can be combined. So here I introduce some new objectives and constraints in order to modify the topology optimization problem and see how it behaves in terms of performances and numerical discretization with an isotropic mesh adaptation. For the objective function here, we choose to minimize the mismatch between the homogenized value that we compute by means of the density variable rho and the targeted value of the stiffness tensor. So what we are doing here is we are minimizing the mismatch between a wanted value and a computed one. So we are targeting what we want to observe at the macro scale by moving the density variable at the micro scale. So here there is a computation of a mismatch, and we are seeing what happens at the macro scale when we observe the micro scale. So small and big scale are intertwined in the objective function. We apply the homogenization theory to move from the periodic micro scale, so the small scale, to the homogenized scale, the macro scale, by means of the homogenization theory. So what we actually do is we observe what happens at the small scale, and we retrieve what can be inferred at the macro scale. And this can serve as a constitutive law for our state equation that is set in the periodic macro scale and micro scale that can be useful in order to compute all the quantities that are related to the design process. So here, again, as you can see, the topology optimization problem is still in the framework that I presented in the toy problem of the minimum compliance problem. But, and again, the protagonist is the density variable rho, but here I change it completely, the objective function that I'm using and the state equation that are governing the physics system, and also the constitutive law that we are employing. But nevertheless, this works again as expected if we want to design, for example, auxetic materials. So materials with negative Poisson's ratio, we can target the property Poisson ratio and set it to minus 0.7. And by means of our topology optimization technique, we are able, for example, to deliver a final result characterized by an homogenized value. So what we see at the macro scale characterized by a Poisson ratio of minus 0.54 and a volume fraction of 0.5. Again, you can see that mesh adaptation, the anisotropic mesh adaptation, well follows the directionalities of the boundaries of the unit cell that we are describing, and is such that we limit the computational resources that we are employing by ensuring accuracy. Of course, all this machinery can work if we change the targeted property. Again, you can design, for example, another oxidic material with a different Poisson ratio, or also you can determine different metamaterial in presence of different properties that you want to impose. And again, mesh adaptation works fine in identifying the boundaries of the structure. Moving on, as I told you, topology optimization in this framework seems to be a problem where you can add or remove blocks that are interesting or less interesting to you. That's why you can eventually end up in a multi-constrained framework and also to a multi-objective framework, because you want to impose more and more constraints on your performances, on the performances retained by your structure, or also because you want to impose several design constraints on the particular design that you want to obtain. Here in this first part, I will detail the stress constraint optimization. In particular, we change the toy problem in order to include additional physics constraints, so that our final structures behaves as we want, not only in terms of compliance or not only in terms of stiffness, but also in terms of other features, for example, the stresses. You can also add many other constraints, for example, related to vibrational frequencies or other things of interest, but keeping in mind that you can add as many constraints as you want, at least until your problem is well defined and you can obtain some solution in the space that you are constraining. So here I will deal with the minimization of the mass. So here I change a little the building blocks of the topology optimization. I want to minimize the mass, and I want to impose two constraints, one on the compliance and one on the stresses. So I impose two additional extra inequality constraints that can be written in the form: compliance should be less or equal than an upper bound, and stress should be less or equal than an upper bound. Once we can write down these quantities in terms of the density rho, we are able to actually start again all the procedure and see how it can work. So the compliance is already defined and it corresponds to the work done by the external forces. While for the stress norm, we employ a gamma norm, an L gamma norm of the von Mises stress that has to be properly modified in order to account for the presence of the density. So again, here in the von Mises definition, we introduce the density variable rho that tells us where that in the portion that we are dealing with, the material is present or void is present. So once you have all these things written in terms of rho, you can start again your machinery and see how it works. So numerical results. If you only activate one of the two constraints, so only the compliance constraint, you can obtain a given design. For example, here in the L-shaped domain, you can see that if we only constrain the compliance, we can have this design, the adapted mesh, the corresponding adapted mesh, and the stress distribution where we can spot, or maybe it is too small, we can spot a stress peak in correspondence of the corner, the internal corner of the L-shaped domain. If we conversely only activate the stress constraint optimization, we can see that we have a different topology, and in particular in the close to the internal corner of the structure, we can see that we have removal of material in order to relieve the structure to be too stressed in the internal corner. But the two structures are only complying with one requirement at a time. If we activated them both at the same time, we can have a stress and compliance constraint optimization where the structure, the final design structure again is different with respect to the other two obtained previously, and also the stress distribution is such that complies with the stress constraint, and also the compliance constraint is respected. Again, the mesh adaptation procedure works well in identifying the boundary, but here, for the first time, we introduced a modification of the mesh adaptation procedure, because we saw that maybe if we only consider the density variable to drive our adaptation, it is possible that some parts of the domain are neglected. So we have coarsened mesh in presence of some given portion that should be refined. So if you consider the internal corner, we are able to locally change the metrics, so the mesh adaptation procedure, in order to enforce an isotropic behavior with given spacing, so that we are able to resolve correctly the stresses in the portions of the domain corresponding to the internal corner. So we are able to identify automatically where we want to modify our automatic mesh adaptation procedure, and can intervene in terms of isotropic mesh or whatever we want to modify our metric bit. So here, all our simulations are reliable because in the presence of the internal corner, we are able to introduce an isotropic mesh, which is able to resolve the stresses. And finally, because I think I have run out of time, 3 minutes more maybe, I can address the problem of manufacturability constraint, as already Charles has introduced you to. In particular, there are manufacturing constraints that one has to address when designing structures in an optimal way. And in particular, the overhang, the presence of overhangs is an issue that many people are facing in the additive manufacturing community. So there are structures that can be self-supported during printing, and there are structures that cannot be self-supporting while printing. So we should avoid to design structure that they have too steep boundaries given a certain threshold. And that's what we do with our formulation. Again, we had another building block, which is not related to the physics, but to the design. We add an additional design constraint. And in particular, what we want to do here, there is a picture which is explicative. We want to determine the portions of the domain where we have overhang, so where our threshold is overcome, and we want to limit these portions of the structure. So we impose a manufacturability constraint in terms of a inequality constraints. We compute this quantity P, and we impose an upper bound on it. And this can be done by means of a shifted heaviside function that takes into account the building direction B and the threshold angle alpha. Again, if you use your topology optimization sim framework, you can obtain some result. And as Charles already pointed out, this can be very bad sometimes, because there are some the so-called dripping effect, so non-actually manufacturable pieces of your structures. When you turn to adapted grid, you can retain the same topology with a better definition of your boundaries, but also you can have an oversimplification of the final layout. As you can see here, when we use a threshold angle of 45, we can obtain a simplified topology by using mesh adaptation that can be detrimental in terms of performances, but also can be good in terms of final layout, because the definition of the surfaces is high quality, and there is no noisy and no dripping effect. Here, so you can see that the use of mesh adaptation does not compromise the design resolution, and in particular is able to relieve some of the problems related to dripping effect of the geometric manufacturability constraint that we are imposing. Also, there is no noisy boundaries in our configuration, thanks to the use of an isotropic mesh adaptation that gives us clear boundaries. And to conclude here, I sum up what I talked to you about. I presented a way to automatically assist structural design problem in terms of, particularly in terms of topology optimization in different scenarios. In particular, I coupled topology optimization with shape optimization. I employed the machinery for the design of metamaterial and to enforce some constraints on the performance of the mechanical performance of interest and also on the manufacturability. Finally, we are working on a different application and extensions of this work to many other fields and application. In particular, we have already worked on a reduced order modeling of for topology optimization via POD approach. We are carrying out a comparison of topology optimization by means of different methods, for example, level method and sync method. And we are trying to use adaptive and hybrid remeshing techniques in order to have reliable finite element discretization. Also, we want to extend what we have done through the 3D case, for example, in the metamaterial scenario. We want to combine the macro scale and the micro scale approach into a multi-scale topology optimization problem. And also we want to deal with more in detail with additive manufacturing, process optimization, and design related. Finally, we will move to applications to more challenging engineering problems, comprising multi-physics and multi-objective optimization. And this has already been done and is an ongoing work with different collaborators. Here I want to name Thales Alenia Space, who provided us with this test cases for a satellite component. Also I want to name MetaMath at Politecnico di Milano, which collects different expertise from the academia, and also Massimo Caraturo and Gianluca Laima at the University di Pavia, who are working with us on new topics for topology optimization and in multi-physics context. Here's to conclude, and just a brief commercial. There is a new work published that would have been suited for the for this workshop as well, but I had to make a choice. So if you want to take a look, it's an isotropic adapted mesh for image reconstruction and segmentation for 3D dimensional medical data. And this is actually the end. So thank you for your attention. And if you have any curiosities, questions, concerns about what I've told you about, please feel free to ask.
Thank you, Nicola, for the nice talk. And so we are running a bit out of time, so I propose to split immediately the discussion, and so Charles can remain here in the main room, in this room, while Nicola can move to the coffee room.
Okay.
And so Luca is inviting all of us to enter the coffee room. You can choose to enter and then come back here if you like. So if you want to make some questions to Nicola, move to the coffee room, and we will resume at